Ho described his multi-stage dynamic system in 1969. Okay, that's the last one I knew about, so apparently somebody found someone even older that invented backpropagation. And in 74, Werbos claims he invented it. 86, Rumelhart, Hinton, and Williams. These guys kind of became the godfathers of neural networks, and they really popularized them in the 80s and brought backpropagation into the public. What matters more, inventing it first or making use of it and establishing it as a popular thing? I don't know either. Depends what you're doing it first, what you're doing it for. I don't know. I kind of like these guys. They did a lot with it. But who knows who to credit backpropagation with? Being first is certainly important in academic communities. So there you go. Here's what backpropagation is. Wouldn't it be cool if we could train the whole darn thing? I mean, it's kind of nice to initialize with random values and train only the output layer. It saves us a lot of computation. But wouldn't it get even more accurate if we could mess with the weights in every single layer and produce a whole network that was as effective as we could get it?
Since you can train the last layer, why don't you then, once you train the last layer, make the second to last layer the last layer, and then train the layer before that?
Huh. So, very good question. Turns out these nonlinearities throw that off. So yes, you can do that. You can train the last layer. If the last layer is invertible, then you could feed your labels backwards through the last layer, and then you'd have labels for the layer just before it. And then if that layer is invertible, you can feed the values back and proceed like that. And it turns out you can do that as long as you don't have nonlinearities here. So if every layer is linear, yes, you can iteratively train one layer at a time, and you can use OLS and compute the optimal weights, and you can train the whole darn thing. But in the end, it's no more powerful than if you had just one layer. If you have any nonlinearity at all, it screws up the math. And I guess here's as far as I'm going to go. If you want to see it, give it a try. Sorry, you'll fail. Essentially, well, actually, this will come out in a proof we'll do really soon. But if you have a nonlinearity, it's possible for the previous layer to rotate to a perspective whereby, see, if you have something nonlinear, you can always look at that nonlinearity from some angle, and it becomes non-monotonic. I don't know if that makes any sense. Let's draw that out. This function is monotonic, right? The more you go to the right, the more up your output is. Yeah, but that's only true as long as your x-axis is right like that and your y-axis is right like that. If your x-axis starts looking like this and your y-axis starts looking like that, all of a sudden you're kind of going down and then up and then back down again. And now if you want to invert the thing, suppose this is your y value. What is the corresponding x value? Well, it could be here, or there, or there, if that makes any sense. And that's exactly what linear layers do, is they rotate stuff around and look at it from whatever perspective they want to. So the optimizer is going to figure out how to look at this in some way that blows your mind. Turns out it's unsolvable. And the more layers you get, the more exponentially large number of solutions there are. It's been proven that optimization with nonlinear models is NP hard. What that essentially means is don't even waste your time. You're not going to solve it. It means that even if P is equal to NP, meaning even if we have a non-deterministic Turing machine, which we don't, but even if we did, have an infinitely fast computer, it would still not be possible to solve an optimization problem with a nonlinear model in polynomial time. So give up now. It's hopeless and futile. Having said that, don't give up now. It's not hopeless and futile. I hope you'll discover something new and make a little progress on it. It's still a very interesting problem. But how could we go about finding the weights for this whole darn big complex network? Well, the answer is going to be backpropagation, and we're going to spend the backpropagation propagation. And we're going to spend the next while deriving back propagation and understanding it, and then we'll code it up, and then you'll have a multi-layered neural network that will beat the pants off of your linear regression model. And that's when the class starts getting cool, in my opinion. So thanks for making it through linear layers, but now we're getting into the hardcore cool stuff. And now we're reaching 1980 something, and hopefully by the end of the class I'll bring you to 2000 and something, and then we'll go from there. Okay. I've gotten a little ahead of myself though. Let's find an iterative optimization process. Is anybody familiar with Newton's iteration? Yeah, there's a few of them. So here's some axes, and here's a thing, a curve. Let's suppose you want to find where this curve intersects the y equals 0. How do you do it? You pick a random starting point. How about right there? Then you take the derivative of that location, and you basically compute the tangent plane to that, or the tangent to that curve. It's really easy to compute where a line intersects 0, right? So you compute where this line hits 0, and that becomes your new point, and now you're right here. And then from this new point, we recompute the tangent line, and it looks like that. And that gets us really darn close to the spot, and then we repeat. And just after a few iterations, a very small number of iterations, we converge very, very quickly to the answer of where this curve intersects 0. Has anybody seen that process before? Okay. It's a cool thing. That's not the approach we're using. I brought it up to start you thinking about how we can use derivatives to get to something. What we're actually interested in is minimizing or optimizing. We want to find the minimum, not the 0 intersect. Why? Because what we have is an error function. It tells how bad our model is, and we want to minimize that, right? Okay. How are you going to minimize? How are you going to find that minimum? Take the equation, you find its derivative, you set it equal to 0, and you do math, right? That's great, but when your equation is the equation for this thing, the number of places where it's equal to 0, well, it's probably going to be 0 if your data is big. But it's going to result in math that you just can't solve because there's all kinds of complexities that come up. I should try it just to prove it to you. But I'm not going to today. Maybe some other time. All right, I need to close my windows. I have too many open. How about this for an approach? I kind of mentioned this earlier. Let's suppose we take a marble, we put it right here, and we just let it roll. It's going to go down to right there, right? Suppose I take my marble and I put it right here, and I just let it roll. Going to go down to right there and stop, right? But what if I put it right here? Well, then it's going to go this way and fall down there. But as long as I get lucky, or maybe if I try enough times, or I start over from enough starting points, and I know how to code up a marble in math, basically this process would work, would it not? Okay, this is the approach we're going to use in back propagation. But here's what it really looks like in reality. We're not going to intersect 0, because 0 means perfect accuracy. And usually we're working with problems where perfect accuracy is not possible. Okay? Suppose we're trying to predict what kind of pizza a person will like. Is there any chance that given 3 attributes that we measure from a person, like their age, their shoe size, and their hair color, we can predict with 100% accuracy what kind of pizza this person's going to like? Not a chance, because there's always going to be a redhead that likes pineapple and another redhead that doesn't. And unless we have enough data to really characterize these people effectively, you can't get perfect accuracy. So imagine a sum squared error curve that looks like that. And because our model is nonlinear, it probably actually looks kind of like this ish. And what we're going to do is we're going to take our marble. We're going to pick a random starting point, and we're going to keep adjusting this marble, and it will roll down, and get stuck right there. And we'll say, there we go, we have a trained model, and that's the best we can do. Or if we randomly start right here, it'll roll down to there and get stuck, and we'll say, there we go, that's the best we can do. Or if we start right here, it'll roll down to right there and get stuck, and we'll say, there, that's the best we can do. Okay. This is kind of disappointing, isn't it? I mean, iterative optimization works, but if your model is not convex, it doesn't seem to find really great local optima. But there are lots of mitigating factors here. For some reason, and this is just kind of hard to explain, backpropagation works really well with neural networks, and nobody's entirely sure why. So here's what we suspect. We suspect that a lot of error surfaces actually look kind of like this. And the idea is, maybe if we roll down the hill, yeah, maybe it gets stuck right here, but the best possible result is right there, and this is good enough, isn't it? Maybe. Okay. It can be disappointing that local optima is a problem, but for some reason, empirically speaking, backpropagation just seems to work really well. So let's see how it's done, and then we'll reason more about its effectiveness later. How about that? Okay. Yeah, so that's another thing. You can jitter it. You can do something called simulated annealing. There's all kinds of techniques that we can use. We'll talk about some of those techniques later. But here's the really interesting thing about it. The more people have used them, the more we find that it doesn't really help much to do things like jitter. For some reason, just doing plain old backpropagation works really well. In fact, let me make one argument for that. Do you remember how with my silly paper example, I was able to separate those x's from the o's with a flat plane just because it was in lots of dimensions, right? Well, if I have this neural network, what is the dimensionality of the weights vector? Yeah, it's big, right? Count up all the lines in there, and we're getting in the hundreds. A lot of neural networks have weights into the millions. Well, imagine a bowl in a million-dimensional space. What are the requirements to be in a local optimum? You have to have a wall on every single side, right? Well, what are the odds of having a wall on all 2 million sides? Chances are pretty good that one of the sides will have a way you can roll through it, right? So now, if you can bend your brain a little bit, imagine an error surface that's complex and nonlinear, but as long as there's one out of millions of possible directions, one way to roll that's downhill, you're going to find it. So now the ball's going to roll and then turn right, and then roll a little more, and then turn left, and then roll a little more, and then turn in the 712th direction, whatever the heck that means. Because you've got so many ways it can turn, because you're in million-dimensional space, it can usually find a way to wind its way down to a really low spot. And so for some reason, just rolling with the gradient seems to result in pretty good optimization, even with darn complex models. Or I mean, especially with darn complex models. Okay. So let's start by going back to our linear model. Linear models create these elegant, beautiful, convex error surfaces, which we take advantage of in OLS so we can compute the exact spot. But suppose we want to do iterative gradient descent with a linear model. It will always end up in the bottom because there are no local optimum with a linear model. how would we do this? We have the equation y is equal to mx plus b. Here's what we're going to do. Wherever the ball is, we're going to compute the derivative. The derivative is the slope of the tangent plane at that point. You remember that from calculus? Okay? And then that tells us something really important. Another way to write the derivative is the partial of h of x with respect to the partial of x. In fact, I want to go with respect to the w, and I'm going to change this to h of w comma x, right? Our model is a function of both the weights that we have for our model and the inputs that we're feeding to it. Now, if we differentiate our model with respect to the parameters of that model, this is what we get. And does this seem reminiscent of something you've done before in calculus? Okay. Well, what this is this is the slope of the partial derivative of the hypothesis, the model itself, with respect to one of the weights, or all of the weights in the model. In other words, we're answering the question, if you change one of these weights, how does that change the output of your model? You see that? In fact, I take that back. We don't want to change that. We want to do it with respect to the sum squared error, which is a big, more complex equation that contains our model. Imagine we could differentiate the sum squared error function with respect to the weights. And first question I want to ask is, can you differentiate the sum squared error function? Yes, you can. We know that because that's how we calculated this thing. Remember, we started with the equation for sum squared error. And then right here, the first thing we did is we took the partial derivative of that, and then we worked out the partial derivative of that. So this ordinary least squares thing is just about the same process. We're going to take the partial derivative of the sum squared error with respect to the weights, and that will answer the question, if I change the weights just a little bit, how is that going to affect my sum squared error? Knowing that is useful because in this case, do you see how I have a negative slope? That negative slope says if I make the weights a little bit bigger, the sum squared error is going to get a little bit smaller. And if I make the weights a little bit smaller, that means my sum squared error is going to get a little bit bigger. Do I want my error to be bigger or smaller? Smaller. Therefore, my weight should get bigger. Okay, so what I have just computed is I should go in that direction. And when I do, it will fall down to here. Okay, now this looks a lot simpler in this 2D space that I've drawn. Now imagine, if you will, a hyperdimensional bowl. So we've got a great big n-dimensional bowl, which you're going to imagine in 3 dimensions because that's all your human mind can handle. So now it's a 3-dimensional bowl, but it's really a million-dimensional bowl. And you compute the derivative of the sum squared error with respect to the weights. There's a lot of weights, right? So we're going to compute it with respect to each of the weights. When we do it with respect to this weight, it tells us whether this weight should get bigger or smaller. And with that weight, it tells us whether that weight should get bigger or smaller. And what we've compute is what's called a gradient vector. And the gradient is a big vector that basically says how much we can change each weight to make the sum squared error change by a unit amount. In other words, it points downhill. Does that kind of make sense? We'll talk a lot more about that, but if you had a big surface and you were at some point on this surface, wouldn't it be nice if you had a magical compass that always pointed the direction that went downhill the most? Well, if you always go downhill, you can basically toboggan down the hill until you end up at a local optimum, and once you get there, you have trained the model. Okay, So I wanted to derive this for a linear model, but I only have 2 minutes and I can't possibly do that. So in 2 minutes. I guess what I've done is I've given you an overview of where we're going next. We're going to use multi-layer models. We're going to compute backpropagation, which is it basically is the derivative of the whole darn neural network with respect to its weights, or of some squared error with respect to its weights. And we will step in the downhill direction until the thing is trained, and that's what makes our model powerful.